Continuing, let's look at our next problem, x squared times cosine x. Now, look at this. Very similar to what we saw in problem number 1. A power of x, but not a fancy power. It's not like a 4x cubed minus 6x plus 1 quantity squared. It's just a simple x to a power. And then my cosine function, this couldn't be any more basic. Again, little things, everybody. We have to be so clear. There are huge differences between these two problems. This one is an integration by parts, a multiplication that I can't clean up, no little quick manipulations, no good choices for a u substitution. I'm gonna use integration by parts. But you go back over here, this also has multiplication, and it also is multiplication I can't multiply or simplify or clean up in any way. But when I get over here, now I see more of an inner-outer setup. So if I try u as the inner, my du will give me the x squared that cancels from this, and this u substitution will work here. But there is no good choice for u here. So again, everybody, we want to be clear. It's not just now we have multiplication, it's multiplication of simple functions. That's what we're really going for. So if you should go and be able to finish this one on your own. That's not bad. I'm just going to end there. That will work as a u substitution. But over here, we've set up integration by parts. Well, how do I assign u and dv? Well, based on the previous problem, the power of x seemed like a good choice for u, which would leave dv as the default everything else, so cosine x dx. And again, this is one that kind of happens to match up, integral u dv, that they kind of match where they, what we want, what letters we want to assign them to, they kind of already fall in that place in the integral. But again, a lucky coincidence. We're not trying to use that for any good fact or reason. So I take my derivative here, du, I get 2x dx. The antiderivative of cosine. Be so careful here, everybody. There's so many extra plus minuses that people goof with sine and cosine because they accidentally take a derivative when they meant to take an anti. The anti of cosine is plain old sine. So when I set up my formula, and again, everybody, when you're first doing it, it doesn't hurt at all. Keep writing out the formula. Remind yourself of it. If we are in class, I would absolutely expect this to be memorized. You should not have any hesitation spitting this out. At home, you get a little more practice, but a part of using the formula well is making sure you keep track of where everything goes. And you'll get that good practice by writing it out, not by just going back and looking at it, but by writing it out, that repetition. So we're looking at u times v, so x squared sine x, minus the integral v times du, and just again, cleaning that up a little bit, v times du, I'm going to write as 2x sine x dx. And now, with the wrong experience, you might say, this is not working. You would go and say, well, look, you had multiplication before, and you still have multiplication. But here, this is a lesson, and it's similar to L'Hopital's rule. L'Hopital's rule, you don't always just do one round. You may need multiple rounds, but you need to see progress in some way. Hopefully you're seeing something good happen, and maybe, again, there we saw the same thing. Sometimes it's just decreasing powers of x. And this is what we should notice here. This and this seem like they have similar problems, but the issue is, well, one of the issues is that, well, again, they still have multiplication, they're still simple, but hopefully what we realize is that this is better because the power of x has gone down. So I'm not giving up here, I'm just saying I'm going to do more integration by parts. Tiny little things. Some people, the book loves kicking the 2 out in front for something like this. I think it's much nicer to leave the 2 as a part of your u. So I'm going to let u be 2x, and then dv would be the leftover, the sine x dx. du is 2dx. The anti of sine, again, the antiderivative, now we'll get a negative cosine. The derivative cosine is negative sine, so that extra negative will keep me positive. And when I put this together, don't lose this piece. Still here, still a part of the answer. Even though it came from the first round of integration by parts, still is a part of the answer. Minus, big set of parentheses. Now I'm applying integration by parts here. But again, it's not just minus the uv, it's minus the whole formula. Minus this integral, so minus the uv minus integral v du. So minus u times v minus the integral v du. And just the little things, everybody, I hope you realize those little things. Instead of being so literal, minus cosine times 2dx, just to kick the 2 out in front. The minus, I already moved in front to make that a plus. Now I'm going to distribute this negative, get rid of these parentheses to make this a plus. And now this is back to a minus. And finally, we're still looking at this, and we see more progress. We had multiplication of simple functions, still had that multiplication, but the power of x went down. Now there is no more power of x. Now there is no more multiplication. And our final answer, don't forget this. We still have this part. And then here, the anti of minus 2 cosine is minus 2 sine. And now technically, if you've been keeping, we could literally have like 5 plus c's. Plus c here, plus c here, plus, I guess 3 was really the most. But don't need multiples, just save it for the very, very end. We don't need a c1 here, a c2 here, and then a c3 at the end here. Just 1 plus c at the end. A definite integral, bounds, those bounds be plugged into all of these pieces. If you want to check your answer, well, you've got some derivative work, product rule, and simple. But like we saw in the previous one, you can go through and do it. You'll see lots of stuff cancel. I mean, just right off the bat, the derivative here is 2x times a plane sine. Eventually, you'll get a 2x times a negative sine when you take this derivative, and those would cancel. The second part of this derivative, this times the derivative, that would be the only piece left behind at the end, and that would match. So again, you can certainly verify that for yourself. I mean, little things, if you do have a little accidental goof with a minus sign somewhere with the sines and cosines, hey, these things happen. So now when you check with your derivative, it's not going to look like it worked. It's only a tiny little mistake. So again, be careful. We don't want to beat ourselves up too much over a silly little mistake like that, but we also don't want to lose little points and frustrate ourselves when it is just a little negative that we forgot. Okay, let's move along. I could go back and do the same thing if I accidentally flip these. If you thought u was cosine, then dv would have the x squared. The derivative of cosine would be negative sine. That's a neutral move, okay? X squared to 2x, that's a move that gets better, but taking a derivative of cosine and getting negative sine, or what we saw back in this first one, taking a derivative of an e to the x and still getting an e to the x, that's not making things better with a derivative. That's a very neutral move. You're kind of shifting from a function to here, it's almost the same function. Here, you would have gone from cosine to sine, but again, that's not improving things through du. So now, again, more experience, still have several more problems I want us to do. Number 3, let's look at the integral x cubed log x dx. People see this one, and now people, again, they think they're seeing a pattern. We had an x e to an x, and that was one round of integration by parts, u was x. Then they had, well, x squared cosine x. This ended up having 2 rounds of integration by parts. First u was x squared, then u ended up being an x. I guess I should point out right here, back in this one, when you're using multiple u and v's, you know, I think my work is pretty clear. This work set up this formula. Now this work set up this formula. Some people don't like using u and v again. So they change it. They make it a db, right? They do an integral. They just change the letters. The integral a db equals ab minus the integral b dA. So you could change letters if you need to, but as long as you're being neat with your work, hopefully we don't have too much problem. We don't accidentally go like this u with this v, right? We keep this u and v together and this u and v together. So just little things just to make sure you're keeping your work neat. But again, people see the wrong things. They go, okay, u is x squared. It took 2 rounds of integration by parts. They come down here and they go, okay, he wants me to do 3 rounds of integration by parts. And they go, yep, u is x cubed. du 3x squared dx. I'm decreasing the power of x like he said, like we've been doing. But then they get over here. You're stuck. You don't know the antiderivative of log. So that's why I said almost all the previous ones we've done, we are picking as something that would simplify with its derivative, and then dv was the default everything else. But that extra note, you need to be able to take the antiderivative of this. Now again, plenty of people just make the mistake. They go v is 1 over x. That's the derivative of log, not the antiderivative. That is garbage. You don't know the antiderivative of log, so you can't even try plugging in the rest of the formula. By choices, we've seen some choices, it works, but it doesn't make your new integral any better. So that's something to be aware. Here we're just seeing this setup just doesn't work at all because I can't complete this. I can't find v. So none of this must have worked. So by default, I must try the other way. Natural log x must be u because at least I know the derivative. And then dv, well now by default, the x cubed is going over here, the x cubed and the dx, because it's everything else and we know the anti. Now you could do du, and that's what we know. We knew the derivative of log is 1 over x. Some people might argue that that simplified sum, I don't know about that exactly, but it's just something that works. It's frustrating because especially the deeper we go into calculus, the more you hear that. Why do you use that? Why do you do that? The answer is because it works. How did you know it worked? Because we tried. So I mean, these little things, you have to know what works. You have to know what to try. So we're trying, and let's keep going. The anti of x cubed is x to the 4 over 4. Now with this setup, u times v minus the integral v times du Now again, if we look too quickly, people would say, well, this didn't work either. We had ugly multiplication here. Now we've got multiplication, or some might say division, and oh, it didn't work, but you went too quickly. Again, all this is this better? And this is really a Calc 1 problem. This may look ugly at a quick moment, but realize we could cancel an x. I'll just do this off on the side here. I'm going to kick the 4 out in front as a 1/4. The x to the 4th over x is an x cubed. So this, it may not have been quite as nice as, say, this integral, where it was just literally a simple function with a known antiderivative and we were done with everything. When we get this new integral, sometimes we got to work a little hard to solve it, and that's why I keep saying we have to know all of the techniques that came before so that we see this and we say, yes, this is working because I could do this, and now I can finish. This part's been done. Here, this will be a minus 1/4, and the anti would be another x to the 4 over 4. So I'll write that as a minus x to the 4 over 16 plus c. And again, a derivative. Use your derivative, use product rule correctly here, no product rule here, and you'll see some good, nice stuff canceling, and that's all that would be left. Okay, so still seeing a lot of little different situations, but everyone so far has been multiplication of simple functions. Lots of times, if we have x to a power, that's my u, but now we just saw one where that setup just couldn't be made to work. So we had to try the other setup, and it ended up working out pretty well because this integral was not so bad. Okay, I still want to do a few problems when it's one simple function with a known derivative and unknown anti, but I want to finish with one more of these multiplication of simple functions. This is quite interesting, everybody. Number 4, we're going to look at the integral sine theta, cos theta, d theta. And what we are going to see in this problem, if you want to do a follow-up on your own, take a look at e to the x cosine x dx. What happens in this one will be very similar here. And by the way, everybody, everything I'm doing, there are very similar examples in the book. Some people, this is a very good base to start with, but before they jump into the homework, having a few more problems, either from our textbook or Dr. Yee's book, having a few more with the full solution, so you get a little more practice on your own before you jump into the homework. It's not a bad idea at all. But we look at this one. And now, if you're clever, you can see a u substitution will work here. It's not obvious, but right off the bat, I've got multiplication and I can't clean it up. If you think about u subs, a lot of people might skip over that here because they don't see a clear choice. If this was sine cosine cubed, well, now cosine is the inner function of an inner-outer situation, and that is your u substitution. And by the way, that u would work. Sine cosine cubed, u equals cosine, is the correct u sub. And by the way, we'll get more practice and reminders. This is a pure trig integral, so we'll get some reminders of similar things in 7.2. So there are several things that'll work here. And that as we go forward, you know, we do have problems. Everyone we've done up to this point is a tailor-made integration by parts problem. And then we'll have other problems that, again, are almost entirely made to take advantage of a particular technique. But some overlap. Integration by parts will work here. A trig integral works. A basic u sub works. But let me just try a trig. Let me try integration by parts. And look what happens here. Here you'd have choices, here you would not. But even right off the bat with integration by parts, how do you pick u and dv? Well, there's no great setup here. We can try with our basics, but eventually we just got to try something. So let's try u is sine, so by default dv is cosine. du is cosine theta d theta. Sorry about that. The derivative of sine is cosine. And then the anti of cosine is sine. You started with this integral, u times v, sine squared, it's literally sine times sine, minus the integral v times du, and here's where people say, wait a second, this didn't work. We keep saying integration by parts, this new integral should be better than the original. Not only is it not better, it's literally the exact same thing. Aha, that is actually a good thing. And this is a weird thing when you first see it, but think of it like solving an equation. If you had x equals 4 minus x, how do you solve that for x? You bring this x to the other side, make it a 2x, and then divide divide the other side by 2. And actually, let's just make this a 10, just so we don't have too many 2's floating around. And that would give me x equals 5. Realize, the same thing happens here. This integral is what we want. equals this minus that same integral. That's actually a good thing. We can add that to the other side. So now I have 2 integral sine cosine equals sine squared. Just like here, when I added the x, I added this integral, just like here I added the x. So now I have 2x equals the whatever, and then divide by 2. Well, 2 times this integral equals whatever. Divide both sides by 2. The only catch with this is that now we didn't finish by solving this integral in a traditional way, but this is still the antiderivative here. So not to forget, you still need the plus c. So, like I said, there are other ways. You might say, well, wait a second, if I picked u as cosine, I got cosine squared over 2 plus c. It's true, but there are trig identities that we could play games and make those into the same function. Use 1 minus cosine squared equals sine squared. That extra 1 is just an extra coefficient. I'm sorry, just an extra constant. So don't let that bother you. That's why, like we said, there were multiple ways to solve this. But here, there would not be. Here, you do your u and your dv. You would feel like you don't make progress. Your new integral would not be the same. You do it a second time, and then you get that same integral, and then you continue with this strategy. So that's a little weird, okay? Definitely want us to see that. We get a lot of integration by parts that falls very nicely and neatly the way numbers 1, 2, and 3 did. Very nice setup. Things work out very nice and neat. But here's a little bit of a funky one. And number 5 is another one that has a little bit of a, again, I don't want to call it weird, but just a little bit of a twist. If this was x e to the x squared, it's a u sub. We talked about that in problem number 1. I think we had a minus x squared, but it was right there. That worked. Here, well, it's tempting from what we've seen to let u be x cubed, and then dv has to be everything else. And people go, okay, sure, so this is working, du 3x squared. We've done this before. We've seen the power of x going down and talked about how that is making good progress. So you feel good, but then you come over here and you're stuck. The key to this is you can't just have this piece by itself. This takes even more clever work. You have to think of x cubed like this. This is going to need a u substitution. You're going to need u equals x squared to solve this antiderivative, but you're also going to need an x that'll cancel with your u substitution. So now with this setup, now off on the side, now this u substitution works. You do get an extra 2. You'll get 1/2 e to the u du. So v will be 1/2 e to the x squared when you finish this part. But notice, you needed that x to make this antiderivative work. Some people, I have seen some help books that talk about integration by parts, and they focus so much on dv. All the little things to make sure that what you set up for dv, you are setting yourself up with a good antiderivative so you could finish the box and set up your formula. So e to the x squared wasn't enough. It needed the x so that this u substitution would work. So I had to take an x away from here. So du, so u is now only the x squared. Du is 2x dx. And now this integration by parts works. U times v. I'm sorry, let me first, before I have the integral set up, first uv 1/2 x squared e to the x squared minus the integral v du. The 2 and the 1/2 would cancel. And this is the second time we've seen this now, everybody. Maybe even the third, but I know it's at least the second. You have a new integral that is identical to something that you already solved going from dv to v. So that still looks a little ugly, But again, if you did all the work to get here, you don't miss this. You already did this part. So our final answer here would be the integral of this is this. So I get minus 1/2 e to the x squared plus c. I will point out there is another technique that some people use here. They realized how key this was. But now they realize there's another little trick they could have applied. Right off the bat, with the original integral, they saw that inner outer. So it's not quite as obvious. This is not that multiplication of simple functions. That is not simple. So it's kind of a lucky coincidence that integration by parts worked here. But again, now we've seen it. So we realize we've got that possibility. But for a lot of other people, there's a clever u sub that works here. Right off the bat, people make this u sub. But when they make this u sub with this for du, one x cancels, but they still have two x's left behind. So that, let me do this on the side here, so that this original integral with this setup, I'd have integral x cubed e to the u du over 2x, 1/2 out in front. That becomes an x squared e to the u du. And normally we'd say, well, that u sub didn't work. You couldn't entirely convert x's into u's, and you can't leave x's and u's mixed together. But here's the lucky coincidence. What's left behind is exactly what we defined as u. So some people can really stretch this u substitution to work. It became 1/2 the integral u e to the u du. And now you'd say, well, why is that better? Now that is multiplication of simple functions. You've converted from x's to u's, so now be careful with your u dv. Now you got multiple u's, and you have to be careful. So maybe now, just to make this easier, make these w's. And now you can go back to your u is w, dv is e to the w dw, and now when you finish solving and back sub to the beginning, you still used a little integration by parts, but you did it in the more straightforward way after making a clever u substitution. So, two things here. Basically, this problem points out the techniques don't exist in a bubble. It's not just integration by parts. It might be integration by parts, and we need a little u sub just to complete this. Or integration by parts, and we needed a u sub to finish this new integral. Or we started with the u sub, got a little clever with our u sub, and then made this into a basic integration by parts. So again, lots to practice here. We definitely want to get good experience. And now I still have two more left to finish, because we've done lots of multiplication of simple functions. Even if they're not the simplest functions, we've had lots of this experience. Let's finish with this. So let's think about which number are we up to? This will be number 6. We will solve the integral of log x dx. That is just one simple function. There's no multiplication. There's not much to this function at all. But the problem is I don't know the antiderivative. But at least I know the derivative. That's my second setup. Similar are both of these. They're all these. They're kind of, then again, don't be fooled. There's no exponent here. That's just the notation for inverse tangent, inverse sine. This one is entirely done in your book. So I'll leave that one, that if you want to try it on your own and then match up with the book to make sure everything worked out, you'll see it's very similar to the one that we'll do together. So we'll do this as number 7, but let's start here. Well, okay, what to do? Well, I'm telling you, integration by parts has a good possibility of working here. But if we're going to use integration by parts, how do we set everything up? Well, dv, we have to know the antiderivative. The whole reason for us doing this is we don't know the antiderivative, so the log has to go here by default. Well, then dv has to be dx by default, right? It still has to be everything else. So not bad here. The point of picking this as u is that I know its derivative. Over here, this one almost seems too easy, but don't forget there's really a 1 here. So what's the antiderivative of 1 dx? It's x. So when I apply the integration by parts formula, u times v, I'm getting x times log x. Again, you notice I keep cleaning it up as I plug in. There's no problem if you write log x times x, but don't combine those x's. Don't make that log x squared. That's where people, if they don't write things in good form, they have temptation to do things that they're not allowed to do. And again, more frustration. Maybe that completely throws off the problem. Maybe it's just a little bit that throws off your answer, but it's all coming from something that we can't do. So I clean that up so there's no extra temptation. That's as good as it gets. Minus the integral v times du. And this kind of looks like that first time we saw a log in a problem. I believe it was number 3. That initially looks pretty ugly until we realize, nope, it actually is very pretty. The x's cancel entirely. Again, the x log x part was done, minus the integral of 1 minus x plus c. And it's an easy example, but realize, like I just said, this integral to go from dv to v is exactly what you ended up with inside of here. Last one, number 7. Let's take a look at the integral inverse sine x. Same thing. There's no choice. I can't make inverse sine dv because I don't know the antiderivative. But I do know its derivative, so it goes in for u. The derivative of inverse sine, 1 over the square root 1 minus x squared, and the dx. The anti of dx is x. So I get u times v minus the integral v times du. All I'm going to do right now when I multiply v times du, I can't cancel, but I'll put the x on top. Does that look familiar? It should. When we discussed inverse trig, and especially when we started to review its antiderivatives, we point out problems like this. If this is a 1 over this, the anti is inverse sine, but x over this, we've got division, we've got inner outer. I'm going to try a u sub. And that's the thing, everybody. Now that we're in this last situation, this has to be better. I mean, right here, number 6 or number 7, or look at inverse tan. You don't know the antiderivative. So anything is better. Here, that looked just a little multiplication cleaned up quickly. This is ugly division. It doesn't clean up, but it has to be better. It has to be better because it's something that's not this. So, but how do we solve this? This is not easy at all. We need a u sub. Here, we'd have to let u be what's inside the radical. Du, there's the extra x that's going to cancel with this. Again, I'm doing this work on the side, everybody. A lot of messy work here. I have my u dv set up here. I'm working on this integral, but all of this is my answer. So let me just work on this integral on the side. So minus the integral x over u to the 1/2 du over negative 2x. As we said, the x's are gone. That becomes a plus 1/2 out in front. That's a u to the minus 1/2 on the inside. Again, the u substitution did a lot, but we still had to bring it up. I still have to use power rule to solve. And now I will back sub. So all of that, the minus I had into account here, it became a plus u to the 1/2. plus 1 minus x squared to the 1/2 plus c. Again, not the easiest problem. That one was quite tough, and that's why I strongly encourage you to take a look at the inverse tan problem. It works out very similarly. U is inverse tan, 1 over x squared plus 1, dv is dx, v is x. You get x over x squared plus 1. Now it's u as the denominator instead of u as the inner part. You get a log of u here. So it works out very, very similarly.